Hello, my name is Dr. Bryan Mendez. I'm an astronomer at the UC Berkeley Space Sciences Laboratory. And this is the time of year when the Gregorian calendar is about to turn over. And so a new year in the Gregorian calendar is about to start. And I thought it's a nice time to kind of remind ourselves of what do we mean by a year? What is a year? How do we measure time? And what does a new year even mean? So I'm going to talk about first a couple of other units of time and build up toward the year. So we'll first talk about a day and how we measure a day. And then I'll talk about a month and how we measure a month. And then I will talk about the year and how we measure a year. And I'll talk about not just the Gregorian calendar, but other calendars around the world. So you can get a sense of, what do we mean when we talk about year and start to realize that in fact, a year is somewhat of a cultural construct and the scientific construct is a little bit different from that. So let's start simply with the basic unit that our calendars tend to keep track of, and that's the unit of a day. And for days, usually we're thinking about them in terms of the sun. The sun is actually kind of the most important object in the sky, and its motion, along with the motion of the moon, are kind of the motions that people for ages have watched and counted in order to keep track of time. So the daily motion of the sun is what we use to measure days. And the way you measure it is kind of up to you. It depends on what's important to you. And a lot of people can consider, for example, counting a day from sunrise to sunrise, right? That could be a period of time that is called a day. It could be one sunrise to the next sunrise, or it could be one sunset to the next sunset. You could choose one noon to the next noon, or you could choose one midnight to the next midnight. The problem with midnight, of course, is that it happens when the sun is not in the sky, but in fact, when it's opposite of noon in the sky. It's when noon is happening for somebody on the other side of the planet. That's actually the starting point that the universal time that the Gregorian calendar is based on uses now. So midnight is in fact the beginning of our days, which is a little counterintuitive because again, it's not something you can directly observe. But if you wanted to choose, for example, sunrise to sunrise or sunset to sunset, one of the things that you discover is that the length of your day is going to vary across the year because as you're well aware, days, for example, are a lot shorter in the winter and a lot longer in the summer. So that means that sunrises, for example, are much later and sunsets are much earlier in the winter. And so your day length is going to vary quite a bit if you measure your time from sunrise to sunrise or sunset to sunset. If that doesn't matter to you, then that's a perfectly fine way to measure your days. If you care about it and you want your day lengths to be as consistent as possible, then the best one to choose would be noon to noon. You can measure noon very simply. In fact, you don't need to have any advanced astronomical objects. All you need is a nice straight stick and stick it in the ground. Make sure that it's pointing straight up and down. You can do that by just hanging a little weight off it. And as long as the weight hangs directly down with the pole, then you know your pole is straight up and down. And then just watch the shadow of the pole move as the sun goes through the sky. And when the shadow reaches its minimum length, that's when the sun is at its maximum height in the sky, and you've got noon. And so that's your noon time. Astronomers call this the transit of the meridian. The meridian is an imaginary line that divides the sky between the eastern and the western halves of the sky. It kind of runs from the north to the south through the apex of the sky, also known as the zenith. That imaginary line is called the meridian, and the transit of the meridian kind of divides the day. And so in fact, you're familiar with the terms AM and PM. AM, of course, usually refers to the morning and PM to the afternoon. AM is an abbreviation for the Latin ante meridian, which means before the meridian, and PM is post meridian, so after the meridian. So when the sun is before the meridian, it's the morning, and when it's after the meridian, it's the afternoon, and of course, right on the meridian is noon itself. And if you measure the amount of time it takes for the sun to go from one crossing of the meridian, one noon to the next noon, that's going to give you the most consistent length of time. Now, of course, the reason that the sun is making this motion through our sky is the Earth's motion itself. The Earth's physical motion is spinning. The Earth spins on an apparent axis that seems to run through what we call the geographic poles in the center of the planet. And that spinning gives us the apparent motion of the sun through the sky. And so any variation in the noon to noon measurement of the day is going to alter two factors. One factor would be the Earth's spin itself. The Earth's spin is not entirely constant because the Earth's mass is not always evenly distributed. And in order for a completely consistent spin of an object like the Earth, you need to have its matter always consistently distributed. But you know, the Earth is made of a lot of squishy, movable stuff. There's water and air and magma, and even the rock itself moves around with tectonic motions, and that causes the spin of the Earth to vary a little bit over time. It's pretty minor. Most of the changes add up to just milliseconds of change in time. So it's a pretty consistent way to measure. Now, one of the things that we can do is not just measure time by the sun, but we could also use the stars. And so we'll want to make a differentiation between measuring the motion of the sun through the sky versus the motion of the stars through the sky. So when we measure noon to noon, sun crossing the meridian to the next crossing of the meridian by the sun, we'll call that a solar day, but we'll also use the term synodic. And synodic in astronomy refers to periods in the sky that are relative to the sun. So since we're talking about a solar day, then that's a synodic day. In this diagram that we're showing here, we've got our starting point 1. We've got this arrow is at one place on Earth. It's pointed directly at the sun, and so that's noontime for that point on Earth. And then the Earth will spin, but as it spins, it also orbits the sun. And this diagram is, the proportions have been greatly exaggerated. The Earth doesn't move nearly this much in a day. And of course, the scale is way off here. But we're just trying to illustrate this notion of rotating and moving at the same time. And because of the motion of the orbit, when this point on the arrow gets right back around to the same spot that it was before, it's pointing off in the same direction, so the Earth has made one complete spin, but it's not pointing directly at the sun, which means the sun is not yet at noon, and so you haven't completed a solar day. In order to complete a solar day, we have to continue to spin just a little bit more, and then we reach that noontime. And so the amount of time that we call a solar day is from point 1 to point 3 on this diagram. Now, we call it a mean solar day because the Earth's orbit is a little bit elliptical, just a tiny, tiny bit, and that causes the speed of the planet around the sun to change ever so slightly throughout the year. And so that actually changes how long it takes to get from point 1 to point 3. And so across the entire orbit, it's not completely the same. It varies by up to 30 seconds either way. And what we do is we define the mean solar day. So it's the average amount of time to get from point 1 to point 3 across an entire orbit around the sun for Earth. And so that we define as 24 hours exactly. So exactly 24 hours is the mean solar day. Now, if we decided to pick a star, let's say a bright star like Betelgeuse in the shoulder of the constellation Orion, and we watch it go through its cycle in the sky. So we watch it transit the meridian and then wait for it to come back to that same transit, we'll find that that was equivalent to a slightly shorter time, which is the same as points 1 to 2 in that diagram that we were showing. So a complete spin of the Earth can be measured relative to the stars because the stars are so far away, they're essentially a faraway reference point. You can think of them as creating a reference grid in the sky, the stars do. And so by watching the stars, we can get a measure of how long it takes the Earth to actually spin once on its axis. And it's a little bit shorter than the solar day. Its period is 23 hours, 56 minutes, and 4 seconds. So just about 4 minutes shorter than the mean solar day. Now, the next unit of time that I want to talk about is the month. And the month is based not directly on the sun, although it turns out the sun is involved, but it's based on the motion of the moon around the Earth. So in the case of the day, that's the motion of the Earth as it spins and as it orbits the sun. The motion of the moon around the Earth will help define what we call a month. As the moon goes around the sun is always off in this one direction. It's always lighting up the moon and the Earth. And so there's a day side and a night side of Earth. There's a day side and there's a night side of the moon. As the moon moves around the Earth, we see different parts of the day side of the moon. And so those lead to what we call the phases of the moon. When the moon is directly between the Earth and the sun, we don't see any of the daytime part of the moon. So we're only looking at the nighttime part of the moon, and we see nothing. And then we see increasingly more until we get to 0.5 here in the diagram, where the moon's opposite the sun in the sky, and we see the entire daytime part of the sky, or part of the moon, sorry. The amount of time it takes for the moon to go through the whole sequence of phases from 0.1 back to, so from a new moon back to a new moon again, that is on average about 29.5 days. It varies a little bit because the moon's orbit has some funny little motions that we won't go into for this little talk here. Now, most of the world's oldest calendars, in fact, used the month. I mean, of course, they use days. Days is kind of basic, but then months were the next most basic thing that you find all ancient calendars using. And you'll see that they often, in order to make up for the fact that it's about a half a day, 29.5 days, they'll vary their lengths of their months from 29 to 30, 29 and 30, back and forth, so that their months will stay roughly synced up with the sequence of the phases, right? So that the full moon will always happen on roughly the same day in each month. Now, as you might have guessed, because I brought it up the last time, I brought it up for a reason. There's a difference between measuring the motion of the moon relative to the sun and measuring the motion of the moon relative to the stars. So a sidereal month would be measured by the stars, and a solar or synodic month is related to the sun. And you might say, well, we didn't talk about the sun. I'm like, yeah, we did, because remember, the phases are due to us seeing the part of the moon that's lit up by the sun, right? So new moon occurs when we have the moon directly between the sun and the Earth. And a new moon occurs after one full orbit of the moon, which occurs after some period of time in which the Earth itself has moved quite a bit along in its orbit around the sun. And so that means when we complete one full orbit around the Earth by the moon, the Earth has moved enough that it's not yet in the new moon position. So one full orbit of the moon, as you might have guessed, that's going to be measured by the stars, and that's a sidereal month. But the full solar month, or what we call a lunation, the phases of the moon, the full sequence, is a little bit longer. So in fact, the orbital period of the moon is shorter than the sequence of the phases by 2 days. So the orbital period is 27.3 days, whereas remember the sequence of the phases from new moon to new moon, from this point, 0.1 to 0.3, is 29.5 days. Now, most calendars, astronomers might think of it would be fun to use a sidereal calendar where you're keeping track of everything relative to the stars, but most calendars you ever encounter on the planet Earth that people have come up with will be based on the sun. So that's why lunar months tend to be 29 or 30 days long, not 27 days long. Now the sun, the sun's motion in our sky also goes through another period of changes, not just the daily rising and setting, but there's what we call the seasonal changes, which are due to the Earth's overall orbital motion around the sun. The Earth goes around the sun in 2 dimensions, which define a plane. We call it the ecliptic plane for reasons that are not totally important right now. But the Earth's spin axis is tilted relative to that plane a little bit, about 23.5 degrees away from straight up and down. And this motion around the sun will make the sun's appearance in our sky change with a period which will actually roughly define a year for most cultures. Here's another view of it. This is kind of top down, and I should have mentioned in that previous picture that, of course, again, proportions way off. This top-down view helps remind you that the Earth's orbit is nearly completely circular. The seasons are not caused by the changing distance, but rather by the changing amount of daylight hours that we get because of the tilt, and also the angle at which the sunlight strikes the ground, again, because of the tilt. A solar year would be the measurement of time from when it takes to get from one of these special places in the orbit. And so when Earth's axis is tilted, when the North Pole is tilted most away from the sun, that occurs in December 21st or 22nd. We just passed that. That's the winter solstice. When the tilt is kind of neither toward nor away from the sun, we call that an equinox. It happens in September and March. And then when the northern hemisphere is tilted most toward the sun, that happens in June. That's a summer solstice for the northern hemisphere. It's opposite, of course, in the southern hemisphere. So you could measure how long it takes to go from, say, the June solstice or the summer solstice in the north back around again, or pick any solstice. From this solstice all the way around to the next occurrence of that solstice, we would call that a complete cycle of the seasons, or a solar year. Sometimes it's also called the tropical year. And it is, of course, a measurement by the sun, so it's also a synodic year. That is 365 days, 5 hours, 48 minutes, and 45 seconds, or 365.242, and let's just round that off to a 2 there, 2422 days. All right, that's the value that we know of the solar year. Now, as you might have guessed, there you can also measure relative to the stars. And so that might, one way you might do that is to say, okay, when I am in this position in September, I'm looking at the sun, I can see that it's located relative to these stars in the constellation Leo, and I count how long does it take for the sun to come back around the sky to that same position. That would be a sidereal year, and as you might have guessed, it's slightly different. It is, in fact, a little bit longer, 365 days and 6 hours, 9 minutes, and 9 seconds. One of the things that's kind of fun to figure out is how many spins do you suppose the Earth makes in one orbit around the sun? And you might look at this number and say, well, it's 365 days, so it must make 365 orbits, right? Well, let's just calculate it. Take the number of seconds that you have in a sidereal year and divide it by the number of seconds in a sidereal day, and you will get 366. There are 366 sidereal days in one sidereal year, and that is the number of spins that Earth makes. So Earth spins 366 times every one orbit around the sun. And in fact, remember, measuring by the stars gives you the best measurement. So the sidereal year is actually the amount of time that it takes for Earth to complete one orbit around the sun. Now, you might wonder, why is the sidereal year different than the synodic year? I mean, I kind of got why the other periods were different, because the Earth was moving around the sun at the same time that either the Earth was spinning or that the moon was orbiting it. But why should the synodic and sidereal times be different? Well, it turns out it's because the tilt of Earth is not always pointed in the same location in space, but in fact it slowly moves around in a big circle. We call that motion precession. You can see that motion in a top if you spin it, or a dreidel. You spin the top or the dreidel, and it'll start to wobble, and that wobble is called precession. The Earth does the same thing. It has a fairly long period. It's about 26,000 years. And that adds up to a difference between the sidereal and the synodic years. It's a pretty small amount, as you saw before. It adds up to about 1 day difference every 71 cycles. So every 71 tropical years will give you 1 extra day in the sidereal period. One of the things that this actually leads to is it changes the date in which the sun is in the constellations. And for those of you who know things about the old-fashioned what's called solar astrology, the idea of the sun being in a certain constellation and being important. That, when it was first thought up by Ptolemy in 2,000 years ago, actually means that the date in which the solar alignments occurred is different now. It's in fact a whole month off than it was 2,000 years ago because of precession. Now, as I mentioned, some of the most basic calendars, or I shouldn't say basic, but the earliest calendars on Earth were lunar calendars. And so a lunar calendar that's just straight up lunar is going to just count the number of times, the moon goes from new moon to new moon. But if you wanted to create a calendar that was tracking both the sun and the moon, you got a problem. And the problem is the fact that there's not an integer relationship between the amount of time it takes for the moon to go around the Earth and the amount of time it takes for the Earth to go around the sun. And because of that, you can't fit an even number of days into a month, and then therefore an even number of months into a tropical year. And that means you're kind of doomed to have a calendar that's going to be irregular. And so a lot of people tried to figure out ways. There was an ancient Greek astronomer named Meton, who lived in Athens, Greece. And he had calculated and realized that there was a close ratio. It's not an exact ratio, but every 6,940 days, you get almost exactly 19 tropical years and almost exactly 235 phases of the moon. So that's called the Metonic cycle, and some calendars try to use that, but it isn't exact. In fact, every 10 cycles of this, so every 190 years, it would slip by 1 day if you were trying to construct a calendar that was using the Metonic cycle. Now let me introduce you to a few different types of calendars, some that use lunar cycles and some that use solar cycles and some that use both. So let me start with the Islamic Hijri calendar, which is purely lunar. And that's also, there are other calendars like that. The Hebrew calendar is another calendar that's purely lunar, which means it has only months which are linked to the phases of the moon. And it does not link to the phases or the seasonal motions of the sun at all. And therefore, 1 year in the Hijri calendar is simply defined as 12 months. So 12 lunations, 12 cycles of the phases of the moon is a year. And in some of the traditions that use the Hijri calendar, they in fact employed an astronomer whose job it was to look for the first appearance of the crescent moon, and that would start the month. And you had to wait for the official word from the astronomer that, yes, I have seen the crescent of the new moon, so therefore the next month can now begin. And in fact, the crescent of the new moon is one of the symbols of Islam. And that's, you can see the connection there between the way they keep time. Sometimes a lot of more recently, people will tend to just use lookup tables. So they'll just create a table of when lunar phases should be occurring, and they make sure that the months are appropriately have either 29 or 30 days to keep it synced up. The Islamic year is therefore shorter than the tropical year. Tropical year is 365 and some change, whereas 12 times 29 and a half days will get you up to 354 or 355 days, depending on how close you're trying to match the phases. So that means that the tropical year and the Hijri calendar will be out of sync with each other, and they only come back around every 32.6 tropical years. So for example, if you're looking at when does the winter solstice occur in the Hijri calendar, well, it's going to constantly move through the Hijri calendar, and it'll take 32 tropical years for it to come back around and land on the same date in the Hijri calendar. The current, by the way, the start of the Hijri calendar is kind of traditionally set as the date at which the Prophet Muhammad made an emigration from the city of Mecca to the city of Medina. And so it is now, we're now in the year 1442 in that calendar, which means it's been 1,442 years since that historical event. The Chinese calendar is a calendar which is what we call lunisolar. It combines both lunar and solar rules. And so it tries to combine them both. And as you'll see in a moment, becomes pretty complicated because of that. The earliest versions of this calendar are quite old, dating back as much as 1,300 years before the Common Era. But it's changed a lot and been modified over the years. But the basic idea of it is that it's a lunar calendar. Each month is a lunar month, so it has either 29 or 30 days. And the first day, again, is the new moon. And the names of the months are simply numbers. They're just kind of the numbered. It's 1, 2, 3, 4 through 12 in the year. Now, they add a solar rule by stating that, all right, we want to have the 11th month always contain the winter solstice. And so that's going to be our solar rule. Now, because those two cycles aren't exactly matched, that means that there's going to occasionally going to be the need to squeeze in an extra lunar month, because sometimes you will actually have 13 new moons between winter solstices. And so in order to figure that, fix that, you have to squeeze in an extra month. And so every so often, there's a leap month thrown into the Chinese calendar. Basically, you can, if you're trying to figure out when the Chinese New Year is going to occur, the general rule that holds most of the time is that it would be the second new moon after the winter solstice, unless the leap month ends up being month 11 or 12, and that turns out to actually end up being relatively rare, but it does happen. So it turns out you need to know your astronomy to know exactly when the new year is coming. And I will try to just say this as succinctly as I possibly can, because it is fairly complicated. The way it is determined which month is going to be the leap month is it's deep in the weeds of astronomical lore, I should say. The sun, makes a path through the sky apparently based on Earth's motion around the sun throughout the year. And what the Chinese do is they divide up that circle, that path through the sky, into 24 kind of equally spaced stations for the sun. 4 of those stations are the places that we've seen before, the equinoxes and the solstices. And these places, these 24 places, are called solar terms, and every other one of them is called a principal solar term. And the way they determine which month gets to be the leap month in a leap year is the month that does not contain a principal solar station. So that's the way it's determined which one is going to be. And you need to be a little bit of an astronomer to know then which year is going to be a leap year and which month is going to be the leap month. I'll just tell you that the next Chinese New Year is coming up on February 12th on the Gregorian calendar, year 2021. I also want to tell you a little bit about some other calendars which don't necessarily have direct astronomical connections, although they still have the day, and so the day is the most basic unit. But there's a calendar that's very ancient in Mesoamerica. The Maya people of Central America call it the Tzolk'in. Actually, that's its name in Yucatec Maya. But it probably originated with what's sometimes called the mother culture of Mesoamerica, the Olmec civilization. So it may be as much as 3,000 years old. It is a calendar that has 260 days in it, and it's a cycle of 13 numbered days and 20 named days. And so that gives you your 260 total days. As I mentioned, it's not explicitly tied to any astronomical cycles other than, of course, a day. But it is noteworthy of a few things that I'll point out, that it's just 6 days shy of 9 lunar months. There's also an important connection with Venus. Venus is fairly important in Maya mythology, and Venus spends roughly 260 days on either side of the sun as either the morning star or the evening star. There's some other interesting ones. For example, there's some almost completely rational relationships between 260 days and the synodic period of Mars, for example. So 3 Tzolk'ins is equal to 1 synodic period of Mars. And 2 Tzolk'ins are equal to 3 times the period between eclipse seasons. And so there's writings that still survive of ancient Maya scholars that where they have tables, and they appear to be using the Tzolk'in calendar to be able to predict occurrences of eclipses, for example, and deciding whether or not they're going to be, those are going to be good omens or bad omens, depending on which day that they land in the Tzolk'in. Now, the Maya and the other cultures of Mesoamerica also had a solar calendar that was 365 days. In Yucatec Maya, it's called the Haab. The Quiche Maya of Guatemala call it the Haab. Very similar. It has 18 what I'll call months, although they're not exactly lunar months. They have 20 numbered days. And then there's one extra, and then there's 20 numbered days, and there's 18 of those months. And so that gets you up to 360 total days. And then there's one special month, which is called the Wayeb, that has just 5 days in it. Now, 365, of course, is exactly what the tropical year is. The tropical year is 365.2422, if you recall. And that means that the Maya calendar is going to slip. Every 4 years, it's going to get 1 day off. And the Maya often keep track of time using both the Haab and the Tzolk'in calendars together, and those two things cycle together. Every 52 Haabs is equal to 73 Tzolk'ins. And it turns out that it's an interesting day. 13 days slip between this tropical cycle and the Haab cycle during one of those 52 Haab periods. And 13 is a very special number for the Maya. And so some modern Maya people have decided that they will actually insert into their calendars a special 13-day Wayeb that will reset the tropical cycle. And it's actually pretty accurate to do that. We don't have any evidence that the ancient Maya did that. In fact, the ancient Maya seem to prefer the steady rhythms of their calendar rather than having these syncopations that would come from leap days. They just seem to found fractions and uneven numbers to be fairly distasteful. And so they were always looking for nice rational relationships. And one of the things that we've found in some of their ancient inscriptions are some inscriptions that show that they seem to have been aware that 1508 Haab was almost exactly equal to 1507 tropical years. So there's some inscriptions that show half of those cycles, for example. And that means that they would have been aware that the tropical year was 365.2422 days. And it seems that instead of adjusting the calendar, to them, it was simply more important that the calendar stayed steady and they just tracked the changes, right? So they just tracked what date the solstice was going to occur in the next Haab, for example. And they just adjusted for that way. They said, okay, well, we know that the date is going to change, but for them, it was more important that the number of days stayed steady between one cycle of the Haab and the next. So as I was saying earlier, a lot of what goes into making a calendar isn't just knowing the cycles and how long the cycles in the sky go, but it also depends a lot on your aesthetics, what's important to you. And for the Romans, they started out with a calendar that was based purely on lunar cycles, just like the Hijri and the Hebrew calendars are. And eventually, the Roman Empire, as it began to grow, and it needed to sustain its people through agriculture, then solar cycles became more important than lunar cycles, because the cycle of the seasons would help you track growing seasons, for example. And so they created a new calendar that was solar based, and they kept the names of a lot of their months previously. So December and November and October and September, those all used to be months in that previous calendar, and December used to be the 10th month. That's why the DEC is there. December means 10th month. When they created the new calendar, they named it for the current ruler of Rome, who was Julius Caesar, so it became known as the Julian Calendar. And the Julian calendar was meant, again, to be a solar calendar, and so they kind of just did away with any notion of trying to keep it linked at all with the motions of the moon, other than the fact that they had months in the calendar. But the basic calendar is about 365 normal days for 3 years, and then every fourth year you got to add one extra day, 366, in order to try to match the actual tropical year. And so the average over 4 years is 365.25 days for the Julian calendar. And then, as I said, because the Julian calendar no longer tried to keep its months synced with the moon, they instead just kind of went with 12 months, since there's roughly 12 months in a year, but not always. Sometimes there's 13. And or at least sometimes there's 13 new moons, right? And they just distributed the extra days across the 12 months. And they didn't have enough to go around, so February ends up with the least amount of days. And that's the day that makes sense to give the extra leap day to than in the leap year. This is not a perfect solution. It slips every 128 Julian years. So one day a 1 day error will build up every 128 Julian years, difference between the solar year and this calendar. This calendar was used for a good long time throughout Europe, and as Christianity began to spread, the notion of using the numbers of the year to mean something other than when Rome had been founded, or how many years the particular emperor has been in power. There was a monk who tried to calculate when the era of Jesus Christ might have been on this calendar, and then kind of backdate it so that the beginning of what they call the era, the Anno Domini era, the year of our Lord, going back to the era of Christ. So there was a particular monk who did a calculation. We're not exactly sure how he determined when and how long ago it had been since Jesus Christ had been walking the earth, but There's some evidence that he used some pretty funky astrological reasons to do so, and didn't necessarily use as much historical information. Um, but he decided that the year that he was living in was 525, and that became known as AD, or Anno Domini, Year of Our Lord. In English, we often call it CE for Christian era, but it's also because this calendar has become more international and cross-cultural, has often been called CE for Common Era. So the calendar, if you want to count it backwards from the years before Christ, it actually then counts backwards, kind of like a negative numbers. And those years are called BC or BCE, either before Christ or before the Common Era. It didn't, this idea didn't catch on right away. It actually took another 2 centuries before a lot of Europe started to make use of it. One of the things that's kind of quirky then about using the calendar in this way is that they decided that there wasn't going to be a year 0, because that doesn't quite make sense to have a 0 year in a calendar. So when you're counting backwards from the year of the start of the calendar, which is 1, then it's not 0, it's 1 BC. So just a weird factoid about this this era dating, this idea of what year we're in being the number of years since Christ was walking the planet. It's worth noting that the Julian calendar also uses a smaller period than the months, known as a week. There's 7 days in this week, and this 7-day week is something that is pretty ancient. It's been used by the Christian Europe for nearly 2,000 years, and may even predate it in ancient Babylonian or Hebrew traditions. It's quite possible then that the 7 days of the week are related to the ancient Hebrew story of the creation in the book of Genesis, in which the earth is created in 6 days, and the creator uses the 7th day as a day of rest. And so the days of the week are often thought of as representing that mythological story. It's also possible that it has other astronomical connections. The lunar cycle is right, it's 29.5 days. It's close to 28 days, not quite. And so 7 days is nearly a quarter of a lunation, but it's not exact. So it's kind of useful, but not exactly useful for tracking lunar phases. But interestingly enough, there is another astronomical connection in the naming of these days. And you can see it especially in the Latin names for the days. In the ancient times, when these calendars were being decided, the idea of what was called a planet were the objects in the sky that moved relative to the fixed stars. And those objects were called planets. And those were the sun, the moon, Mars, Mercury, Jupiter, Venus, Saturn. Those were the 7 planets, and the 7 days are named after them. And in English, you can it's obvious. Sunday and Monday are obviously the sun and the moon, and then it becomes less obvious the English connection. Although if you dig into Norse mythology, where most of the names of the English days come from, the connections between the characters in Norse mythology are connected to characters in Roman mythology in the same way, and then associated with their appropriate planets. So for example, I don't want to spend a lot of time there, but for example, what we now know as Thursday is in Latin in honor of Jupiter, or who was known as Jove. So it's Dies Jovis, that's Jupiter. Jupiter was the Roman god of thunder and lightning. And the Norse god of thunder and lightning is Thor. And that day is, of course, Thor's day. So Thor's day is, basically honoring the same kind of god, the god of lightning. Now, because the Julian calendar doesn't match the tropical cycle exactly, that means over a large period of time, that 1 day slip will start to add up. And this became a problem for the Catholic Church, who used astronomical motions to set the date of important festivals like Easter. And it was starting to create a problem where, in fact, the Christmas season, known as the Advent season, was beginning to overlap with the Paschal or the Easter season. And that was starting to happen in the 16th century. And so the scholars of the day tried to figure out, okay, how can we fix the calendar so that this won't happen? How can we get a slightly closer match to the tropical period of the sun, and keep the calendar a little bit more closely aligned so that we don't end up with this problem anymore? And this was happening during the reign of Pope Gregory the 13th, and therefore when it was enacted, it was called the Gregorian calendar. And when it was enacted in 1582, it occurred in October in such a way that the last day of the Julian calendar was Thursday, the 4th of October, and the next day was Friday, the 15th of October. So you lost those days in order to kind of catch back up to the sun and kind of reset the calendar. So the first day of the Gregorian calendar was Friday, October 15th, 1582. That actually didn't catch on for the whole world. You know, the whole world wasn't going to use the Gregorian calendar way back then anyway, but at least in Europe, it took a while too. The last country in the world to kind of adopt it for civil purposes was actually China back in 1929. It's the calendar, of course, that we're fairly familiar with. It's the one that's coming to an end here at the end of this week, and then starting up, you know, the next year. The change that the Gregorian calendar made, besides just throwing away those days to catch back up, was to also decide to throw out 3 leap days every 400 years. And then the rule that they came up with in order to do that was, you know, sounds kind of complicated, but the end result is remove 3 leap days every 400 years. And so the rule, of course, is that every 100th year is not a leap year, except for the years that are divisible by 4. So that rule ends up throwing out, you know, that extra leap year, or those extra 3 leap years. And that turns out to do the trick. Over 400 years anyway, that will give you an average day length of about 365.2425 in the calendar. And remember, the tropical period is 365.2422. So we're still a little bit off, but it's close. You know, it's a simple fix. It gets us really close. And it turns out that we're using that little simple fix. You stay pretty tight for over 3,000 years. So, you know, that's a pretty good fix. And so that's the calendar that we use now, and the one that is about to flip over to the year 2021. I should mention before closing out that, funnily, kind of ironically, I guess, astronomers don't actually use the motions of the sky anymore to measure time, because those motions are variable at a precision amount that we now need greater precision for. So we now make measurements of phenomenon that are happening in shorter time spans than the precision of the astronomical motions of the you know, the Earth spinning on its axis, and the Earth and the Moon going around the planet. So instead, we have to redefine time, the basic units of time, and the way we've done it is actually to use transitions of electrons within atoms, in particular the cesium atom, the isotope of cesium that's has atomic weight 133. We had to pick a particular transition that is very, very stable in that atom, and then count the number of those transitions that will get us as close as possible to the current value of the second, and then redefine a second to be equal to that number of electron transitions in that atom. So it turns out that that's what we do. That's what's now called an atomic clock. So now the second becomes the basic unit of time in astronomy and physics. And therefore, the day is now based on the idea that, of course, a minute has 60 seconds, an hour has 60 minutes, which is a total of 3,600 seconds. And therefore, a day is 24 hours times 60 minutes, or 86,400 seconds. And then furthermore, we have to kind of just decide what kind of year. When an astronomer says years, what do they mean? Do you mean tropical year? Do you mean, sidereal year? What kind of year do you mean? We said, you know what? We just mean Julian years, 365.25 days exactly, which is 31,557,600 seconds. And that is precisely how long a year is to astronomers, right? So again, how long is a year? Well, it depends on who you ask and why you're asking. All right. Thank you for listening. If you have questions, you can find me on Twitter at Bryan J. Mendez, and go ahead and shoot me a question. I'd be happy to answer any questions you have about measuring time. Thanks, and have a happy new year.